Researchers in California have come up with a way to move water through a structure filled with holes without it leaking. The new idea uses the power of surface tension and tiny 3D printing called microarchitecture to expose a huge surface area of liquid to the surrounding air. And these kinds of designs could have a huge range of different applications. Liquids and gases are by definition difficult to mould or structure. They need to be enclosed so they don't leak everywhere. But this means it's usually quite hard to get a lot of their surface area into contact with their surroundings. And that puts a limit on how much surface area you can use for important functions like absorbing carbon dioxide or releasing heat. The researchers at the Lawrence Livermore National Laboratory looked at examples in nature which use these kinds of processes, such as gas exchange in the lungs or the movement of water through trees. Trees use capillary action to draw water up from the roots in tiny tubes, a process that depends on the way water molecules stick to themselves and their surroundings due to surface tension. It was this process which the scientists wanted to harness, but to do so without enclosing the liquid seemed impossible. So the team turned to the world of microarchitecture. They used one of the world's most advanced, custom-built 3D printers to print tiny cubic cells of only 1 millimeter wide. These tiny cubes are small enough to hold water without breaking its surface tension, so the sides of the cube can be completely open without the water spilling out, meaning the surface area exposed to the air outside is much bigger. And by stacking hundreds of these tiny cubes together, they created a scaffolding that liquids can climb up without being enclosed. This process only works at exceptionally small scales that were previously impossible to create. Experiments showed the absorption of gases by the liquid in these open lattice structures was up to 3 times faster than the absorption of gases by the same volume of liquid in an enclosed column. And by creating a network of these open-faced cubes and tunnels, scientists think they'll even be able to direct the flow of liquids through a system. The applications of this are immense, from heating and cooling energy-intensive systems like computer servers, to transporting waste carbon dioxide in industrial reactors and returning it as a raw material to be reused. And in space, where controlling liquids is even more problematic, the ability to have contained yet open-faced liquid structures could be groundbreaking for gas and heat exchange. In fact, without the limitations of gravity on capillary action, directing liquids through these microstructures could be extremely efficient. This use of microarchitecture creates systems that are more organised than the chaotic natural networks in trees or lungs. And one day, the scientists hope to combine their models with real living systems, as they achieved with these seeds, absorbing water through a printed structure. Creating hybrid biological organisms with more efficient and more organised features could have numerous applications in space agriculture, tissue growth such as semi-artificial lungs, and atmospheric cooling. A pretty big future for these tiny liquid cubes.